begin to understand solution chemistry, we have to begin with the basics. So, we're going to start with Avogadro's number and Avogadro's constant. So, Avogadro's constant is the number of moles or molecules that are contained in the amount of a substance given by 1 mole. There's a formula, and that's given by N equals M over Mr. Now, this is a very fundamental formula in chemistry. So the N stands for the number of moles, the M is for the mass of the substance, the Mr is for the molar mass of that substance that was given. Now we're going to do an example here. That example is going to be solving for N, so the number of moles of a substance. So we're going to go N equals M, and the mass here is 10 grams, and the molar mass of the substance is 1, because we're going to give the substance the element of hydrogen, so it has a molar mass of about 1. So therefore, this compound, or this solution, has a total number of moles of 10. Now, moving along, Avogadro's number is the proportionality factor which relates molar mass of a compound to the mass of the sample. Now we can use Avogadro's constant, which is 6.022 times 10 to the 23rd, in a bunch of other practical applications, which we're going to go into further in this video. Now, next up we have molarity. Now, molarity is pretty easy. It's indicated by the big M here, and the units for it are moles per liter. So, as an example here, we're going to have 1 mole per liter, which is equal to 1 M. So that means the concentration is 1 mole per liter. Pretty simple. So finally, we can put these two concepts together into one formula, which is C equals N over V. Now, it's a very simple formula. This just means that the concentration is equal to the number of moles over the volume. So now let's do an example using this formula. Say we're trying to find the concentration given the number of moles and volume. Say we have 2 moles and 10 liters. Remember that the formula has to be given in moles and liters. So if you have milliliters, you have to change it. So we simply divide and we get 0.5 concentration, which is equal to 0.5 moles per liter. So now let's dive deeper into some solution chemistry. Now, before we go deeper, we have to know that a lot of solution chemistry with the equations have to do with stoichiometry. So, yeah. Let's talk about cars. Cars are a great example of solution chemistry because there are countless examples of them. So, for example, the outer frame of the car is usually a metal alloy solution of either carbon steel or aluminum, depending on the manufacturer. The airbags are also a solution. So, like airbags, airbag systems contain a mixture of sodium azide, NaN3, KNO3, and SiO2. So a typical driver's side airbag contains approximately 50 to 80 grams of the sodium azide, with the larger passenger side airbag containing about 250 grams. Within about 40 milliseconds of impact, all these components react in 3 separate reactions that produce nitrogen gas. So here under the airbag section we have all 3 reactions, and the first one is left unbalanced purposely because we're going to be working with it as an example. So the first thing we want to do is we want to balance the equation, so we put a 2, and a 3. And that will balance out our equation. Now the next thing we're going to do is we're going to rewrite the equation up there to make it easier for us to work with. So let's try to find out how much volume of nitrogen will be given if we have 250 milliliters of sodium azide. So the next thing we're going to do is try to determine how much moles we have of sodium azide. So we know we have 2 molar, so knowing that, we can put it in our equation. So we use N equals C times V. So N equals 2, and V, we had 250 milliliters, so we have to actually turn that into liters because the V in the formula is given in liters and not milliliters. So we turn that to 0.25, so that's N equals 2 times 0.25, which gets us 0.5 moles. So now all we have to do is put it into a very simple mole-to-mole ratio. So we're bringing the 2 down from sodium azide, the 3 down from the nitrogen, then the 0.5 from the moles of sodium azide that we had. Then we're trying to solve for the nitrogen, so put an x there. Simply solve for x now. So we get x equals 0.75 moles. Using that 0.75 moles, we can use our N equals CV formula and rearrange that for V. So we get V equals N over C. So V equals 0.75 over 3, which we can then solve. So the volume of the nitrogen given is 0.25. So then we turn our 0.25 liters into milliliters, so we can see that given 250 milliliters of sodium azide, we get back 250 milliliters of nitrogen gas. Alright, so let's just clean out our drawing board here. So now let's talk about the remaining reactions in the airbag solution. So, given the sodium that we got from this reaction, it goes on into the next equation to react with KNO3, which then yields even more nitrogen. So essentially this process of the airbag just continually compounds like more nitrogen, so it inflates not only very quickly, but also produces a high volume of nitrogen gas. So now let's talk about fertilizer. So fertilizer is one of the most revolutionary discoveries in recent human history. So it was created by the synthesization of ammonia, and it's used as a fertilizer. So it's created by using the Haber process, which was discovered in 1910 by a German scientist. So the use of ammonia in agriculture has helped to expand the world's potential food supply, which in turn allowed the population growth of the 20th century, but that's irrelevant to chemistry, so we won't talk too much about that. So this process combines 1 mole of nitrogen and 3 moles of hydrogen to form 2 moles of ammonia. Now that we've talked in depth about airbags, how about we actually show you how an airbag works in the lab? So without any further ado, to the lab. We're going to be doing a demonstration of the airbag lab. So what we have here is...
So we have a plastic Ziploc bag that is about 675 milliliters in volume, 13.8 milliliters of 2 molar hydrochloric acid, and approximately 30 grams of sodium bicarbonate.
So what we're going to do is we're going to fold the Ziploc bag in half so that we contain each side with its own chemical. So one side is going to have the hydrochloric acid, one side with the sodium carbonate, and then once we have the two all in there, we're going to hold it here, mix it up a bit, and let the carbon dioxide fill the airbag. And yep, then we'll have our demonstration of an airbag.
So due to the Avogadro's number, we can see that every mole of carbon dioxide will take up approximately 24.5 liters. So this is why we have such small quantities of product. So let's begin.
Alright, so now we're going to dump some of this sodium carbonate into our bag. So let's start off pouring it onto one side of our bag, zipping that side up, folding it over so that none of our reactants mix together before I want them to. So, fold that over. Now onto this side. Zip it up a little more. We're going to pour, here, can you do
the HCl into the other side of the bag.
Alright,
now
we're going to zip it up.
We will completely zip up the bag. Can you zip it up?
Yeah, hold it like this.
Yeah, I got it.
Alright, now that the bag is completely zipped, we'll mix them together and react.
Now you can see there's fizzing already, and this is clear. It's a clear indication that CO2 is in fact rising from the solution.
Now it's an exothermic reaction, so if you feel it, it's giving off heat.
So now we're just going to leave the bag with all the reactants and see it expand. So after a while, you can see that the CO2 that was in the reaction has expanded, and with Avogadro's equation, you can see that it is taking quite a lot of space.
Now, the difference between this and an actual airbag is that this took quite a significant amount of time to fill up, and that's because the chemicals we're using aren't the same as in an actual airbag. So in an actual airbag, this reaction would happen almost instantaneously, hence inflating the airbag very fast.
The reason for this immediate change in volume is because the chemicals that they are using are much stronger and much more reactive, which would be dangerous in this situation. So, as you can see, our airbag was quite successful, and can now withstand a lot of pressure, just as a real airbag would. Thank you.
I'm Savita Paul, and this lab is exactly the way it should be done. Absolutely amazing. Do it.